Hi again and welcome today to Physics 10 class. Today is April 1st and today is going to mark the last chapter that is going to be included in this midterm. So chapters for the midterm are from chapter 1 all the way to chapter 18. I'm working on a review for you guys for this exam, for this midterm. It's going to be immediately after the spring break. So during that time, I should be basically on campus myself. So we have 2 days. One of them is to actually complete a quick, there will be two components essentially for this exam. A component that is quiz type and a component that is basically problem, like the ones that you guys have been working on the homework, where you're going to do that. So again, that's going to be part of the review. The review will have, like I said, a component that is actually graded. It's graded for participation only, in a sense that if you do it, you get full credit for it, regardless of how much you score in it, just to basically encourage you and give you an incentive so that you can go through the review. So this is basically how the this exam is going to be formatted. Again, by next week, you will have a review for the entire midterm, and the midterm covers chapter 1 all the way to chapter 18. This chapter, today's chapter, what we're going to be doing next week in terms of lecture is going to be for the second exam actually, so that's not going to be included in this exam. So again, let me share with you the screen for chapter 18. So again, we're finishing thermodynamics for this section. So this is going to be the last chapter in thermodynamics. Basically, we studied the concept of temperature, the concepts of heat. I even did a demo for you guys. And now we're going to end it basically with the concepts of thermodynamics. Thermodynamics, as I said before, is science that was basically how should I say it, put together. Or at least the person who started it was an engineer, and it has so many ideas in here. One of the ideas at the end, it's really has a lot of implications in almost a lot of branches of science, whether it's physics, whether it's chemistry, whether it's biology, whether it's society in general, and even extends its influence all the way to philosophy. So really the idea of entropy has a lot of implications in a lot of fields in science and basically philosophy and things like that. But it's really the idea behind it as a concept is that heat does not spontaneously on its own move from a cold source to a hot source. That is basically what we have seen. So this is, in a sense, what the idea of entropy is. This turned out, so basically this is the question that Mr. Carnot asked. What is the most efficient engine? In doing so, he wanted to basically to prove what kind of the most efficient engine there is. He asked, grant me this, and that turns out to be the second law of thermodynamics. Grant me that heat does not transfer on its own, does not move on its own from a cold source to a hot source. From a hot source to a cold source, that's normal. I mean, you take a cup of coffee, you fill it up with coffee, hot coffee, and you put it outside and wait for it. Ultimately, heat will leave the cup of coffee to the environment. That's on its own. You don't need anything else. Could it be the other way around possible? No. That is what the second law of thermodynamics. This is very much related to another basically phenomenon. Let's say, for example, you take a plate made out of a glass, for example, okay, or this cup, for example, and you drop it. If you drop it, it's going to fall and break into several pieces, a lot of pieces. This is normal. Anybody who looks at that experiment say, okay, that's fine. I mean, if you find shattered glass all over the place, you know that at some point it was together and somehow it was broken into so many pieces. Is it possible that the shattered pieces of the glass all of a sudden combine and mix and make the cup again or the plate again? Is it possible? If you see that on YouTube, where all of a sudden, for example, pieces of a broken thing, like for example, a glass cup or something like that, now coming together, animated, coming together, and all of a sudden making the cup again, you know that's fake. You know that this is not true. You know that the natural behavior of a cup in this situation is to break into pieces. That's fine. Gravity will take care of that. All you have to do is let go of it and it's going to fall into several pieces, depending on basically its structure. Could it be possible the other way around? You know it's not true. Why it's not? It turns out it has to do with this concept of entropy, not the energy. In terms of the energy, there is absolutely nothing wrong with all of the pieces coming together and basically combining again and then making the whole cup again. So you can calculate the energy and coming from the ground and coming all the way to your hand. This is no problem whatsoever. In terms of energy, there is no problem with it. As a matter of fact, in terms of F equals to ma, also there is no problem with it. That equation, F equals to ma, is 100% reversible. Whether you play the F equals to ma in the forward direction of time or the backward direction of time, it's the same thing. It's always F equals to ma. So there is nothing inherent in the laws of physics that prevents this, with the exception of the second law of thermodynamics, namely the law of the heat cannot spontaneously move from a cold source to a hot source. It can move from a hot to a cold. There is no problem with it. So this is the idea behind this whole thing. And this also seems like this law of entropy has a direct connection with the flow of time. Time seems to be move forward in only one direction. I mean, we can remember things that happened in the past. We can remember, for example, things that happened 7 minutes ago when we started the class, or things that happened yesterday, or things that happened probably a year ago. We have that kind of thing that we have it in our minds, but we cannot remember tomorrow, for example, or we cannot remember, for example, what's going to happen. We cannot remember, for example, spring break, this coming spring break. So there is that thing that seems to be connected with the idea of entropy. So it's really science, and then it's connected to philosophy somehow, and then people twist it all the way to the existence itself and what it means and all of that. So it's a big deal. It's a big concept. This is in addition to F equals to ma that we guys learned from this class. I'm hoping the concept of entropy will be the second one in terms of things that you remember from this class. In terms of importance, probably this concept is far more important than the concept of F equals to ma. F equals to ma will get you solve problems and do all kinds of things. And that is the basic laws of Newton and get you to understand a lot of things. But this one will make sense of things. Chemical reaction, for example. You take hydrogen, for example, and you mix it with oxygen, and you add to it a little bit of heat, and then all of a sudden this two will give you water, H2O. That's a chemical reaction. What makes this possible? That's the second law of thermodynamics. When you calculate the entropy before and the entropy after, it is the one that allows for this reaction to happen. As a matter of fact, an organism, whether a small animal or bacteria, all the way to the most developed one like humans, biology is also governed by this one, the growth and everything else. So this is a really, really big deal when it comes to concepts and ideas that are in science out there. So this is going to be the item of discussion today. So I want you to really think about the entropy and what it means. And second law of thermodynamics, you're going to put it in your own words, the second law of thermodynamics. Basically, two ideas. Either we say that heat does not flow naturally on its own, spontaneously, from a cold source to a hot source. That is the same thing as saying that a system, any system, regardless of what it is, will always evolve in such a way that the state of disorder increases. That is the same statement, actually. And both of them are equivalent. And what it means, okay? What it means on a daily experience. It would be fun to do an actual experiment. Please do not injure yourself by breaking something and play it with a video. I mean, record it and then play it backward. No matter who you show it to, this is obvious that it violated the second law of thermodynamics. So this is basically the item. Let me first of all go back into the share screen. So this is the things about it. Absolute zero, this is the zero temperature Kelvin. This is something else also that is coming from this branch of physics, in the sense that when we were experimenting with ideal gases, gases with low pressure basically, and this started in the beginning of the 19th century, around 1800 something, we noticed the following. The pressure is proportional to the temperature if the volume is constant. The volume is proportional to the temperature if the pressure is constant. And if the temperature is constant, the pressure and the volume are inversely proportional to one another. There are three laws in here, okay? Now, it seems like the product of the pressure and the volume is somehow proportional to the temperature. That's what this law says. So if I take a gas with a given amount of volume in it, the pressure and the temperature will be proportional to one another. Increase the pressure, increase the temperature, the pressure increases, and vice versa. So what happened if I start lowering the temperature? Well, I can lower the temperature, the pressure will drop with it. Lower the temperature, the pressure will drop with it. Lower the temperature further, the pressure drops with it. There will be a point of zero pressure. Wow, as if the entire gas basically is frozen, does not move at all. That is what we mean by the absolute zero. At that point, when the parts of the gas don't move, that means at that point, we have reached absolute zero. Absolute zero is really an ideal situation. It cannot exist on itself. It does not exist in reality. This is a theoretical limit for temperature, which is negative 273.15. Nothing can have that temperature. I mean, look at it from the perspective of volume. You mean keep the pressure the same and drop the temperature, the volume shrinks. Drop the temperature further, the volume shrinks. As you are doing that, the volume becomes smaller and smaller. When you reach that temperature of negative 273.15, you will have no volume. So I ask, what happened to my gas? I had an amount of it, but now it occupies zero volume. So it does not, there is no such a, it cannot do that. Therefore, this temperature is a theoretical limit. Nothing can reach 0 Kelvin. I mean, you can have small number of a Kelvin, like for example, 0.1 Kelvin or 0.01 Kelvin, but you cannot have 0 Kelvin. This is impossible. And there is another justification why this is so, and that is coming from another branch of physics called quantum mechanics. Quantum mechanics will require that no matter how low the temperature is, there is always that quantum, basically, jiggle, that quantum motion. And that is, we're going to make sure that you cannot have zero. You always have some finite temperature, no matter how low, no matter how much you reduce the pressure. You cannot get to 0 Kelvin. By the way, it's called 0 Kelvin. That's what the 0 stands for here. That is the unit of the temperature, which is negative 273.15 degrees Celsius. So that is the concept of the absolute zero. So absolute zero is a theoretical limit, because when you plot the graph for the pressure versus temperature for one gas, nitrogen, for example, and you take oxygen and you do the same thing, and you take another gas, for example, carbon dioxide, for example, and you do the same thing, you will, and of course, Even in those days, they did not reach that temperature. Even today, we cannot reach this temperature. It's impossible. We can reach a lot, very small temperatures nowadays, because we have other ways basically of reducing pressure by basically pumping out more and more stuff. So we have powerful ways of pumping, but we still cannot reach that temperature because it's a limit. We cannot get it. It's like the speed of light. Nothing can travel faster than the speed of light, except light itself. And light has no mass, so no mass can travel with the speed of light. This is also another trick in here that you never seem to play on us, that nothing can have a temperature that is actually equal to 0 Kelvin. So when you extrapolate those dependencies, you will find them meeting at some limit, which you know is impossible. And that limit is negative 273.15 Kelvin. The temperature has no upper limit, though. It has lower limit, but no upper limit. And like the speed of light, and like the speeds in general, you can have no speed whatsoever, but also you cannot have more than the speed of light. You cannot have the speed of light, end of the story. So this is basically the idea behind it. Any system has in itself two kinds of energies, really. It has let's call it this way. It has an internal energy. The way to change its internal energy by one of two ways. Either add heat to it or compress it, do work against it. So that is actually the first law of thermodynamics. The first law of thermodynamics said that an internal engine of a system, internal energy of a system can only be changed by pumping heat into it or actually compressing it and doing work against it. Then there are different ways of changing the state of a system, different ways. You can do it in several ways. One of them, by keeping the volume constant. So this is called an isobaric process. Isovolumetric process, isochoric process, which is the same thing, isochoric or isovolumetric process, meaning the volume doesn't change. This way, you don't do work against the gas, because the gas, in order to compress it, you have to change its volume. Since there is no volume change, in this case, there is no work. You can only heat it up. Okay, like for example, what you do with the pressure cooker. The first thing you do is seal it and then turn on the heat on it. So its internal energy is increasing over time, but in that case, the volume is not changing. So you're doing it at constant volume. So in this case, you're not compressing the fluid that is inside, or you're not letting it actually expand to do work against the environment. So in this case, you're adding heat to it. So that is called an isovolumetric or isochoric process. Another way of doing it is keeping the temperature the same, and that is called an isothermal process. Okay? Isothermal process, for example, is what happened inside the combustion of your engine, the engine of your car. What happened in this case, the mixture of air and fuel mixed together, and then there is a spark. There is a spark plug that basically gives a spark, and that ignites the fuel with the mixture with the air, and that there is a lot of heat that is transferred to the gas at that temperature, which is super high temperature. Gas expands, pushes the piston, the gas moves to another chamber, in which case it gets rid of the heat into the environment, into the surrounding. And then it's compressed again and sent back again. Actually, there is an intake of more fuel and air, and the process repeats, okay? So that's another process at constant temperature, which is called an isothermal process. The third process is called an isobaric process. This process happens at constant pressure. In diesel engines, especially, this is exactly how that works. Okay? In diesel engines, what happened was there is actually a big compression with no fuel in it. So there is a big compression with no fuel, and then you take the fuel at extreme high pressures, and because the fuel comes in with the, of course, air mixture, comes in at extremely high pressures, just because of that, it's going to ignite. You don't need spark plugs for the diesel engines. So, and then it's going to expand and basically do the work for you and move the piston and turn it, and not the piston, I'm sorry, Yeah, the piston and the piston turns all of the machinery inside, and big machines move that way. So that is an isobaric process. Both in the car engine and in the heavy duty engine, they have this so-called adiabatic process. Adiabatic process is basically a process where there is no change in heat. There is no exchange of heat. So that is exactly what an adiabatic process. The adiabatic process during a compression of the diesel engine or an expansion of a diesel engine or a compression of a regular car engine or an expansion of a regular car engine, it happens at so rapid that there is no time for heat to be exchanged. The way sound travels from point to point also is so fast that there is no time for heat to be exchanged during that motion of sound. So this is called an adiabatic process. It's a process that is not associated with heat transfer. It's like, not true, like taking your system and wrapping it in a big blankets, putting it in a big, basically, a place so that it does not lose heat. Or taking your coffee, for example, and putting it in a thermos so that it does not lose heat. And you start doing things with it, compressing it and doing all kinds of things with it. So that is basically what an adiabatic process. So the word adiabatic in this case means that there is no exchange of heat. Obviously, the first three processes I mentioned, isovolumetric process with no change in volume, isothermal process with no change in temperature, isobaric process where there is no change in pressure. All of them involve the state of the system. This one involves heat. And heat, we said, it's actually an exchange between place to place. So it's really not an intrinsic property of the system. So this is actually different. That's why we had to introduce the concept of entropy. The adiabatic process and the concept of entropy are related to one another in a sense that the entropy is actually sometimes, the adiabatic process is actually a process where the entropy doesn't change. It's an isentropic process. That means the process does not, the entropy doesn't change. So now it's just like the other three. It's just like the other processes. Obviously, any system can undergo combination of these four processes, or actually can go in any nonsense process. It can go basically anywhere you wish it to go. But this is how it's broken down into the industry. This is how we operate, basically. These are the four main processes involving a system going from state to state, regardless. When there is heat exchange, of course, when there is temperature involved, when there is a difference in temperature, basically. Meteorology is an example of that, basically, because you have huge masses of fluids in the air that move because of this dynamic. So it plays not just a role in the engines of cars and the engines of trucks, but it plays actually a role, for example, in understanding motion of big masses of air, like, for example, in the case of the weather, or in the case even of the inside of the planets, or inside of big systems, or even the inside of stars, for example, how heat goes from a center to the outside, or even how the entire universe evolves. And maybe this whole business about time has to do with this entropy. Maybe this entire fate of the universe itself is governed by this law. That's why it's important. Because big systems where there is exchange of heat and everything else, and how the universe evolved from a point of a singularity that had tremendous amount of heat that is unimaginable temperature, down to a temperature of slightly over 2 Kelvin, maybe this whole business has to do with that and the fact that we cannot travel in time, back in time, although we have a good memory of it, has to do with this entropy. Maybe the reason why we are traveling somewhere in the future and we don't remember, for example, how tomorrow looks like, is because of this entropy. So that's why it's an interesting topic, okay? The second law of thermodynamics, I gave you the statement for it. Heat does not travel spontaneously from a cold source to a hot source, or any system on its own evolves in such a way that the entropy increases, okay? Order and disorder are exactly what that entropy is. So the entropy is actually, in a sense, a measure of how disordered the system is. Okay. Oh, this is a big topic. So the science was developed in the early 1800s, the 19th century, around 1826 to be more exact. The atomic molecular model was not understood then, so early thermodynamics involved macroscopic ideas such as mechanical work, pressure, and temperature. So we had no idea what those things are, but these things we can measure them. Temperature, we already devised the first law to measure it. I mean, zeroth law to measure it. Mechanical work, we can do that. So the foundation stones are the conservation of energy and the fact that heat flows spontaneously from hot to cold source and not the other way around. So this is your second law of thermodynamics. This is your first law of thermodynamics. And your zeroth law of thermodynamics is what allowed you to measure this. Because pressure, you can measure it. Pressure, all you need is the force over area. So that's measurable. Mechanical work is easy to measure too. It's basically force times distance, displacement. So you can measure these things, okay? So what was left in this thing in here was temperature. So temperature, we needed actually the zeroth law. As I said in the beginning, that we discovered this one first. So that's what Mr. Carno's question was. Then we said, okay, we needed at least a law before that. That is actually more fundamental. It turns out the conservation of energy is that law that is more fundamental than this seemingly easy law, which is the case. So this is the second law of thermodynamics, the first law of thermodynamics. Then after these two were developed, then we came up with an idea on how to justify carrying with us basically a thermometer. So this is basically the idea behind it. So again, I mentioned about the absolute Kelvin. So absolute Kelvin, theoretically, the volume is zero. So if you're asking what happened to the volume, then I had stuff in here. This blue area is that of an object in here that has a temperature of 100 degrees Celsius. So we know that there was stuff in here. I can weigh it, actually. I can weigh this piston by itself. I can weigh this container by itself when they're completely in vacuum, if I can somehow do that. And then I put gas in here, so I know exactly how much this gas, I have gas in there. There is gas in that volume. So if I increase the volume, if I decrease the temperature, the volume drops, and the volume keeps on dropping after I change so at some point, if I do the algebra correctly, I will have a zero volume. So the obvious question is, what happened to my material? Since the material is still there, the gas is still there. Therefore, this temperature in the numerator cannot be equal to 273.15. The exact number is 273.15, by the way. Okay. So these experiments were conducted with the ideal gases that have specific requirements in terms of their density and their pressure and so on and so forth. So we know that there is a lower limit to temperature, and that lower limit happened to be 273.15. For all practical purposes, you just put 273, okay? So energy at the particle level within a substance is several forms, which can be taken together and as internal energy. So every given particle itself, in an ideal gas, it's free from the rest of the other particles. So it's not interacting with the other particles. Technically, there are no potential energy at this point because it's not interacting with everybody else. But it's moving. It can move left and right. It can move up and down. It can move in and out. So it has kinetic energy in the x direction, in the y direction, and in the z direction. Now, if this particle has a finite size, let's say, for example, like in the case of the oxygen molecule or the nitrogen molecule, it's made up of two oxygens or two nitrogen atoms. Then in this case, in addition to the fact that the molecule can go left and right, up and down, in and out, it can actually spin one way like this or spin like this. This spinning doesn't make any sense because the atoms are so tiny that you cannot detect that spinning. So in this case, you have 5 ways for it to have energy. Energy of translation, in and out, or translation up and down, or translation, call it left and right, up and down, in and out, or spinning around this axis, or spinning around the other axis. So that's 5 ways for it to get energy in it. If it is a carbon dioxide, though, or a water molecule, it has actually 6, at least 6, probably more, okay? So the problem gets more and more fun when you have more molecules in it, but it's still, that's the only way for an ideal gas where there is low density so that the atoms do not interact, that it can store energy in it, okay? If it's more dense, like for example, in the case of liquids and solids, then I have to take into account the interaction between individual molecules. Then they have the potential energy. So that is really how you treat this problem in here. That is the internal energy of everything. So if I take one molecule and next to it another molecule and sum up all of this, that is the internal energy of my system added together. So the first law of thermodynamics states that the heat added to a system transformed to an equal amount of some other form of energy. Basically, energy is conserved. So if you add heat, for example, when you take this coffee, for example, and put it in the microwave. Right now it's empty. Actually, let's put in it water, for example, and put it in the microwave, and put the microwave on a timer and turn it on. Each second or a fraction thereof, heat is being added to the liquid in here. Or put the whole thing under the stove, for example, when you use some sort of metallic pot in there. Turn the stove on. So you're adding heat to it continuously. So what you notice in here, the temperature rising. If you put a thermometer in there, you'll see that the temperature is rising. Temperature is actually how much internal energy you have. Temperature is how fast the different particles are moving inside that system. So the fact that your temperature is going up because of the fact that you're adding heat to it, then in this case, the internal energy is increasing. So where is that energy coming from? It's coming from the heat that you have it underneath. So heat in this case is changed to a different form of energy, which is the energy of motion, or it could go to the potential energy, for example, into breaking bonding or doing something in there or strengthening some or doing something to it if you remove heat on. So that is basically how you change the energy of a system. Or alternatively, actually, you don't need to have heat on it. You can compress it too. You will see that its temperature starts to rise. Okay. If you play with the pump, for example, when you're pumping, for example, a balloon, a ball or something like that, you will notice that its temperature change. Or one of those dusters like this one. If you turn it on and you feel it cold because it's expanding so rapidly, taking energy with it in the process, okay? So in this case, it's doing work against the environment, against my hand. My hand could potentially move, actually. So where is that energy coming from? It's coming from the inside. If you touch it, you'll find it cold, okay? Believe me, it's cold, okay? So that is another way of removing energy from the system or adding energy to the system. Did anyone experience with this thing? Exactly. The reason why it becomes so frozen is because of the energy that is coming out from this end. From this end is actually, it can move something, okay? I mean, put anything in there. I'm going to put this one in here because I don't want to. Yeah, it can basically push it. So where is that energy is coming from? It's coming from the internal energy of the gas that is contained. If you feel it cold. So it lost energy in here. It's because of the first law of thermodynamics. Okay? It's because of the first law of thermodynamics. So let me share back again the screen. So that's it's the first law of thermodynamics. At its full glory at work in here. Okay? Conservation of energy. Mr. Joule actually did an experiment because people at that time, they were confused a little bit what heat was. I mean, you take the pot, for example, put it on top of the stove, and you turn the stove on, and now you feel the heat. Actually, you can feel it yourself. When you step out on a very hot day, when you open the window or you feel the heat basically coming and smash you in the face. So you have that feeling on your skin. So you can tell the people, I thought that this is some sort of fluid, okay? They called it the calorific fluid, but they have no idea what that was. So they basically imagine that some heat is some sort of fluid that flows from a hot source to a cold source all the time, because you can feel it yourself and you can sense it yourself. So what he did with this experiment, basically, he dropped these weights. As they move, they turn this object in here around, okay? This one will stir the water. So where is this motion is coming for the liquid in here that is being stirred? It's coming from these two masses that are dropping. He can calculate the energy in this case of these masses that are dropping, how far they drop, times the mass of each and every one of them, times the gravity, which is 9.8. That's how much energy is in there. Then he took a thermometer and he put it in there, and he noted that the temperature was changing, rises, goes up. Water is a kind of a very weird substance to work with. So if you have a different liquid, that's better, because water has a very high specific heat. You need a lot of energy for you to raise it even 1 degree. You need 4,190 joules to raise it just by 1 degree, to see actually, for 1 kilogram, of course, of water, 1 liter of water. So you need that much energy to raise it just by 1 degree. So if the temperature was 20 degrees and you're hoping to make it into 21 degrees, you really have to have them fall very long distances. So this mass times G, which is 10, times the distance it fell in, plus this mass times 10, plus it has to be at least 4,190 joules to see that. Of course, he didn't call it joules at that time. He called it the energy, whatever that, which is mass kilogram times meter per second squared times meter. So that was the unit for it then. He saw, he knew, he discovered that the heat that is added in calories at that time corresponds to the 4,190 kilogram meter squared per second squared, which was the unit for energy at that time. And it was consistent all the time. So heat is energy. This is the Joule's apparatus that he showed with it. From that point on, in his honor, people called the unit for the energy in mechanical energy as in joules. And now calorie, 1 big calorie is exactly 4,190 joules. 1 little calorie turned out to be 4.19 joules. So there is a 1-to-1 correspondence between the two, okay? You experienced these things in here. That's probably the question that Marwan mentioned earlier. I mean, the item that he said in the chat before. Yes. Samantha also experienced the thing there with the duster, don't you? Good. Okay, so that is actually the pump, which is the opposite to it. Okay. Because again, when you compress it, you're doing work against it. Okay, let's go back in here. So when you're compressing it, you yourself, you're working. Actually, you can sweat too. You can just feel you're pushing the air inside, you're doing that. So what happened in this case, you're putting work on the gas and you're compressing it. Where did that energy go? Just like before. When you put it on the stove and you turned on the heat, that heat went into it to increase its temperature. Same thing in here. When you do work on it too, you're going to increase the temperature. So in this case, energy is conserved. Whether you do work on a gas, you add its energy, or you're going to add heat to it, you're going to add to its internal energy, because energy must be conserved. It cannot go, it cannot vanish. Okay, so it must go somewhere, and in this case, it goes to the inside of the system. So that is what the first law of thermodynamics is. In adiabatic compression, compression or expansion, a gas where no heat enters or leaves the system. Basically, it's completely hermetically sealed so that there is no exchange of heat. Then in this case, this process is called an adiabatic process. Sometimes, and this is at least for your own reading purposes, you will find that this process is sometimes called an isentropic process. That means the entropy does not change, constant. I cannot say constant heat because heat is not a property of a system. It's something you add to the system or remove from it. But you cannot have constant heat, doesn't make sense. But the entropy, you can keep it constant. So that's why somewhere else you probably will find it called an isentropic process where the entropy doesn't change. This means the same thing. So in adiabatic, conditions are achieved by thermally insulating a system from its surroundings, performing the process so rapidly that heat has no time to enter or leave the system. So those are the two ways. Either you seal it completely, wrap it in a blanket and do it, or now here is the thing. Do not confuse the two. Constant temperature is not adiabatic process necessarily. I'll give you an example. In the case of the engine, for example, during the explosion, during the time when there is a chemical reaction that provides a lot of heat, okay? So this point in here, it's so hot that the gas starts to expand rapidly in here, pushing the piston basically this way, taking this heat from the explosion, because there is a spark plug that basically ignited the mixture of air and fuel. So now this one is expanding. So it's taking a lot of heat and expanding at the same time. So it's taking heat in the form of having its energy going up, but it's expanding and disposing of that heat that was added to it through work, okay? So it's working. So it's getting rid of that energy actually. So the energy is going up because of the heat that is being added, but it's also going down because of the rapid expansion. So in this case, what's going on? The entire energy is not changing. The gas temperature actually does not change during I mean, when you see it outside, of course, it feels hot. Why? Because it compressed. That during that stage is when the temperature went up. So yes, the temperature was up, but during the explosion itself, at that point, it's taking heat from the explosion, from the residue basically of that chemical reaction between the fluid and the air, and that takes it and expand. So that's why actually during that process, it's a constant temperature. The energy does not change during that process, okay? And this process happens so rapidly that the piston expands so fast, pushing basically the flywheel and all of the other machinery so that it starts turning and turning the wheels with it and the car moves forward. Of course, it happens not in just one chamber. In a 4-cylinder car, it happens in a cycle on different, depending on which piston where this thing is happening. But each one of them helps in the process of pushing the flywheel, and the flywheel turns the whole machinery so that it starts moving. So the point being in here is during that stage, there is a very, very high exchange of heat that then it's taking heat. So it's not an adiabatic process, getting rid of the heat through work so that there is no change in temperature, So this process is at constant temperature, but it's not an adiabatic process. Okay, it's not a process that is at constant heat, because there is heat being taken from that chemical reaction. So don't confuse the two. Believe it or not, this is one of the most things that some of my, even the engineering students, struggle with it a lot when they're doing problems with thermodynamics. So this is something that you have to really pay attention to. The distinction between a process at constant temperature and a process with no change of heat, no exchange of heat. Because temperature and heat, yes, they are related, but they are not the same thing. Okay. So here, heat added to the system, increase in internal energy work is done on the system. So in this case, you're compressing it and you're adding heat. I mean, there is no heat in here, but you're adding work. Actually, you're compressing the gas, so you're adding more energy into it. We're doing on time. Oh man, we still have a lot of slides. Okay. Thermodynamics is useful to meteorologists when analyzing weather. The first law of thermodynamics expresses air temperature rises as heat is added or as pressure is increased. Okay, heat may be added as incoming solar radiation, radiation back from the earth, or moisture, condensation, or contact with the ground. So if the sun starts to shine, basically in this case, heat is added from the top of the clouds, or from radiation from the earth that also can give you more heat. The earth absorbs heat during daytime, but then it delivers it back. Not just the earth, all of the components basically that takes heat. Moisture condensation also is another way of getting heat, and contact with the ground. So that is how the air can have its temperature change. So during no exchange of heat, so the air now moves up and down, and that is during which then the air masses now take with them the energy and lower the energy through the motion in this case. Okay. This is an experimental law. Okay. Temperature drops by 5 degrees every time you climb 1 kilometer in the atmosphere. Okay. So this is basically something that, I'm sorry, by 10 degrees, 15 to 5, 5 to -5, -5 to 15 degrees, every 1 kilometer up in the sky, okay? And this is what happened to the air when it goes around in this case, okay? So it's going to cool down and starts to rain from one side, then in the other side, it's not, the air is moving faster and getting a lot of the energy. So it's warming actually on the other side. So air will expand as long as it has a higher temperature than its surrounding. So if the surrounding has a cooler temperature, it needs to expand. And this is exactly how the air masses move. So on one side, it's cooler than the other one, then the hot air region. So the hot region now need to expand. And in doing so, it's going to change the temperature of the other region. So that's what the weatherman is talking about all the time in here. And there are points in here. The actual mechanics of it, or the dynamics of it, is a little bit more involved, and involves because the air masses in general is really a how should I call it, a system that involves a lot of basically moving parts in it. That's why it becomes a little bit more complicated. But this is in a nutshell, the mechanics behind it is the laws of thermodynamics in this case. So this is the second law of thermodynamics. This is what I want you guys to remember from this chapter, basically, in addition to the first law of thermodynamics, is heat itself never spontaneously flows from a cold object to a hot object. I mean, from a hot to a cold, that's fine. There's no problem with it. But from a cold to a hot, it's not going to happen on its own. So you're asking, what happened in the refrigerator? Well, the refrigerator is not a spontaneous process. If you take, for example, it doesn't matter, anything in there, for example, a cup of water, you put it in the refrigerator, its temperature will go down. And it's going to go down further and further. It becomes so cold, actually, it could go through a phase transformation, becomes solid, becomes ice. So what happened in this case? It was cold already, and now it's ice. So heat flew from the, left the cold source and ended up outside in the hot source. Because if you go behind the refrigerator, you'll find it hot. So heat is continuously being pumped or leaving the cold water to make it even colder and get outside, which is already hot, to make it even hotter. So the refrigerator works backward than this process. And why? Because not a spontaneous thing. It does not go on its own. It requires a, okay? The key word in here is spontaneously, by itself, basically. So again, you can express in terms of the weather phenomenon or any system in here. Heat can flow from cold to hot only when work is done on the system or by adding energy from another source. Case in point, heat pump. Refrigerator is an example of a heat pump, pumping up heat outside. And so is the AC unit, by the way. Both of them are heat pumps, okay? A heat engine, which is an opposite to a heat pump, is any device that converts internal energy into mechanical energy. So a heat engine, this is what it does. You have a hot source. You have a cold source. Takes heat from here. Does work. And get rid of the excess heat in here to the cold source. So this is the dumps heat in here. Dumps excess heat. So this is in a sense what an engine is. A refrigerator or a heat pump, it's the other way around. A heat pump, you have a cold, like a cup of water, and you have the hot, which is outside. You need work in here. That's what the refrigerator does, or the AC unit does. Takes the heat from the cold source. So it extracts heat now. And dumps it to an already hot place in here. So this is where dumps heat to the hot source. So this is a heat pump. Basically, it's pumping up heat continuously. And this one is an engine, a heat engine. Does this models make sense to you guys? Do these two models make sense to you guys?
Yeah, that makes sense.
Yeah, that makes sense.
Very good. They're working opposite to one another. Okay, they're working basically opposite to one another. So in other words, you can take a heat engine and you can reverse it and make it into a heat pump, and vice versa. You can take a heat pump and reverse it and make it into an engine. So all you have to do is put the machinery backward, that's all. Put the plugs in the opposite direction and it should work, okay? Put the wiring in there in the opposite direction, it should work. So the basic idea behind the heat engine is that mechanical work can be obtained only when both of them, by the way, energy is conserved. In this case, the heat that is taken is equal to the sum of the heat that is being dumped plus the work. In this case, the heat, the work that you're going to need, plus the heat that is you're extracting will equal to that. Both of them are the same thing. Both of them obey the first law, okay? And both of them obey the second law too, because this one, you can actually have it without work in here. I mean, we want to get work out of it, but if you let go of it on its own, this is the heat is going to spontaneously move this way. In here, it's not going to happen to have heat go from here to there. You really have to have that work in here. You have to pay for it to have it work, to have it done this way. Okay? So this is the model. This is really what the model is. Okay? So the heat input, this is what the heat engine is. Okay? So it's operating between two temperatures. The temperature of the high source and the temperature of the cold source. This is sometimes used as T hot, and this is T cold. So that is basically the terminology that you will see in there, T hot and T cold. Only some of it can be used to, for an engine, okay? That's why the efficiency of any engine can never be 100%, because some of you probably might be wondering, why do we have to get rid of the heat? Why can't we take all of the heat and make it into work? Well, you want to close the cycle. You want this to repeat again and again and again and again. So at some point, you need to go back to the starting point. So that's why you have to have two temperatures. And at some point, you really have to pay for that price, okay? Not sometimes, you always have to pay for that price, and the efficiency of any engine is less than 100%, no matter what. Here is the deal with thermodynamics, and that's a problem, big time, okay? It's kind of depressing a little bit. The first law of thermodynamics basically says the following. The best thing you can hope for is to break even, because the sum of the energy the sum of the energy added is the sum of the energy that is in the system. Conservation of energy. Conservation of energy requires that basically the maximum you can do is break even. Basically, if you're going to do an effort to do something, the maximum you're going to do is to be 100% efficient and get all of that effort converted into what you need to do. What is depressing about this situation is, so in other words, you can't get anything for free. You can get net more than what you put. So somebody tells you that I put 110% for it, doesn't make sense at all. So there is no such a thing, because you cannot have more than what you input. So you cannot have more than 100%. There is no way. The first law of thermodynamics prevents it anyway. Okay, that's one thing. The second law of thermodynamics says that even 100% you cannot achieve it. That's what the deal is. Because systems in the entire big scope of things must, at the end, obey the second law of thermodynamics. So there are losses due to friction, losses due to moving parts, no matter what. So you can never, ever, ever even break even. So that's why it's a little bit depressing when you think about it this way. The second law of thermodynamics, or the law of entropy, will make it so that you cannot break even. Okay, so you're always basically at the loss at the end of it. I mean, you're losing stuff. Mr. Carnot came up with the most efficient engine, and the most efficient engine of Carnot is not 100% efficient. It's less than 100% efficient. However, and he basically came up with the idea in the 1800s, in the early 1800s, still until today, not a single company out there can beat Carnot's engine, cannot even make Carnot engine, which is the most efficient engine there is. So this cars, Toyota, Mercedes, Ford, all of these makers of vehicles and makers of machinery and everything else, they cannot, first of all, there is no such a thing of 100% efficient engine, even with the best Tesla out there that is running on electrical engine, or Prius, or whatever you can think of as being efficient. They are not 100% efficient, number one. Number two, they are not even as good as Carnot engine. Carnot engine is an ideal engine that you cannot even make, and that's still less than 100%. So it's kind of depressing when you think about it this way. Hey, but we keep on trying. So that's really the whole thing in here. Okay. So this is true all the time. So thermodynamics presents some challenges in real life, basically, that are out there, and they are true for any system, regardless. I kept on giving examples of mechanical system, but this is true also for biological system as any other system. You're asking, oh, I saw an animal that was this small, and then it starts to grow and getting more energy into it and getting more and more organized. It seems like this one is actually becoming efficient and actually becoming more and more organized. So this seems to be in violation of the second law of thermodynamics. Well, if you take that animal by itself, or an object by itself, like for example, the cup of water that you put it in the refrigerator, and you ignore the fact that it's dumping heat outside, the cup of water is getting more and more organized. initially it was atoms moving every which way. Now they are organized. Actually, if you look at the ice, it has a very well organized structure. So now for that specific water, its entropy actually went down. But when you look at the big scheme of things, when you take the entire universe, its entropy actually did go up. For that bug, for example, that was growing, and that animal that was growing, or whatever that system, biological system that seems to have its entropy going down, it is going down. It's getting more organized and basically more. I mean, if you wake up in the morning and the bed is a mess and then you fix it, actually, you have reduced the entropy that way. Okay? Clean up the room, you dust it off, you did everything. So it looks like the entropy went down, and it did go down for that particular room or for that particular bed. But if you take your effort in it and the energy exhausted yourself and all of the moving parts in there, the entropy of that entire surrounding, including yourself and everything else in the universe, went up actually. Okay, even for biological systems, they're still governed by this law. Okay, so this is the ideal engine. This is Carnot engine. No engine can be as efficient as Carnot, no matter what that is. His name was Sadi Carnot. He was an engineer for the French army, and he computed the engine, and this is the efficiency he came up with. There is not a single engine right now that can come up with this efficiency, let alone beat it. Okay? Biological or otherwise. I'm sorry, biological systems, yeah. They have to go through this process and they cannot, okay? This is the most efficient engine there is. This is actually a theoretical engine. You cannot even achieve it in the real life, so forget it then. Okay, so no matter who you are, no matter which company you're working with, no matter which, I mean, you cannot beat Carnot engine. And I know now we have all kinds of microelectronics and devices that use superconductors and semiconductors and all kinds of things out there. And we cannot do something better than this. Isn't this kind of a sad story? But that's basically a fact. It's just like, for example, when you talk about the speed of light being the upper limit for any speed, nothing can move faster than that. That is another limit for the efficiency. Nothing can be as efficient as Carnot engine operating between these two temperatures. Obviously, you have to give me the two temperatures. If it's, for example, room temperature, which is right now, let's say, for example, let's take it 20 degrees, 27 degrees, which is about 300 Kelvin, and 100 Kelvin, which is the boiling of water. So the difference between them is 100 divided by 300 and 300. So it's 100 over 300, that's 33%. So a most efficient engine that operates between the boiling temperature of water, for example, which is 100 degrees Celsius, and room temperature, roughly about 27 degrees, cannot beat Carnot, cannot be more than 33% efficient, cannot be even 33% efficient. It can be 32, it can be 32 and a half. If you are an outstanding engineer, the best engineer out there, and you come up with the most efficient and the cleanest room there is, and you work out with the ideal environment, then probably it's going to be 32.9 or something, but it cannot be 33%. It cannot be as good as this one. Okay. So that is really how this is. Obviously, if you work out with other temperatures and even higher in the temperature, like for example, what's going on in a car, the temperature is much, much higher than that because there is a combustion of the fuel there. So yeah, the efficiency is more than 33%. But then if you compare that one to this engine, it's not going to be that good either, okay? That engine inside a car is going to be less than this one between the same two temperatures, comparing apples to apples, okay? Comparing a Carnot engine at between those two temperatures in whatever engine you can pick up, the VW engine or Toyota engine or Impala engine, whatever engine you can think of. It's all of them the same thing. And when I said Impala, I meant the car, not the animal. Okay. Obviously, not to pick on anything, but the Mustang in here would be a lot worse than this one's in here. Does any one of you drive one of those muscle cars? Good. Yeah. I miss my Prius. I had two Priuses and I traded one of them to the other day for another car, for another Toyota. I think I'm going to get my Prius back. I'm going to get because I like to save energy. I have also still a hybrid, the hybrid RAV4, so it's still okay to some extent, but I want to go back to more efficient stuff. Anyway, so again, the idea of order and disorder are related immediately to the entropy. That's another way of putting it when it comes to the energy in here, to the entropy in here. Okay, so the idea of entropy has to do with the order and disorder, or how much heat is actually being exchanged per temperature, as related to temperature. Both of them are related to. So living organisms take in food or extract energy from their surroundings and become more organized. But if you take it in the entire context, yes, their entropy seems to be increasing, but if you take it in the entire context as that living organism versus the environment, it's still the entropy everywhere is getting higher and higher. So their entropy themselves is going down, but taken in a big context, it's still going up. So entropy can decrease if work is put into the system, but overall it's going to stay up. If disorder increases, then entropy increases. The measure of the entropy is that of the. So the second law of thermodynamics is that the net entropy in the universe is continuously increasing all the time. That's another way of saying the second law of thermodynamics. I know we said it in the beginning that heat cannot transfer spontaneously from a cold source to a hot source, but this is equivalent to it. Both statements are accurate. This is what Mr. Boltzmann basically derived at the end. Right? The formula that is written actually algebraically, you really don't need to know this one, the exact formula, but just to give you something on a culture, so that if you happen to go to Vienna and see his tomb, this is what is written on his tomb. Okay. I think log in the base of 10, but it should be really at the base of E omega. Okay, this is the order and disorder. This is a constant that's actually called Boltzmann constant, and this is the change in entropy. This is always greater than, at best scenarios possible, equal to 0. But that's actually an idealized situation, just like what happened with Carnot cycle. Okay. That's why you cannot really beat a Carnot cycle, because Carnot cycle is where the entropy doesn't change. And that is basically an ideal engine. That's why any engine has to obey with this law. And that's why you can never beat him, because the entropy in any closed system, in any system, because when you take it in the context of the universe, will always have this one change in the entropy more than 0. Hence, because the other one, no, number one. I just said the fact that this is just to, if you happen to go to Vienna and would want to experience the coffee in Vienna, in Austria, and also experience the opera theaters and all of the fun culture in Vienna, this is another thing that you could do. Go to the tomb there of Mr. Boltzmann and ponder on this thing that he discovered for us. Mr. Boltzmann tomb is actually in Vienna. That's where he passed away, and he's the one, a long time ago, of course, the beginning of the 20th century. So that is why some physicists, at least, that's what they do when they go there. In addition to coffee and opera, that's where they go and look at stuff like this one. So this is for your general culture. Okay. Does this answer your question? Okay. I know probably for you, you have another passion just like mine, and some of you guys in here too, and that is to go to the stadium and watch, I don't know, Vienna, Austria, do they have a good teams? I don't know. Anyway. Okay, so this is the thing with the entropy. The net entropy in the universe is continuously increasing, it's always going up, okay? So this is just to put it in what is written on it, at least in there. But the entropy itself is always going up. The change in entropy is always more than 0. That is another way of saying this one. The net entropy in the universe is continuously increasing. The change in it is always positive. of course, it has to do with the probability, because this omega is measures how many states basically a system can have. That's why it's probabilistic theory. Anyway, this is basically in a nutshell your chapter. And please go through the book. Make sure you understand everything in there. And again, I will be posting the review materials for the midterm, starting from hopefully as early as next week. If not, maybe during the middle of the week. And of course, you will have a lot of time to prepare for the exam because of the fact you have a spring break after that one. I know that you probably have plans for the spring break, okay? Please make sure that your spring break includes also preparation for the exam too, okay? Yes. It has to do with the second law of thermodynamics. You have to put it.
Was there just only one assignment?
Yes, only one.
Because I got here late too, so I just want to make sure. So it was like,
yeah, go ahead. Samantha, were you saying something before I said so?
I'm gonna write because I don't have billion.
Okay, go ahead. Only one. Okay. And the item has to do, okay. The item has to go with the entropy, and basically the fact that the entropy is the law where heat does not transfer spontaneously from a cold source to a hot source, and the key word in here is spontaneously. And also it's related to order and disorder in a sense that the system will always evolve in such a way the entropy of the universe always increases. And regardless of what that system is, it could be a biological system, it could be a mechanical system, a chemical system, a planetary system, the universe as a whole. So the whole thing is really governed by this law. That's why I think that's probably far more important for your general education and knowledge than even the laws of Newton, which are very, very important up to this section. When we're tested on the exam, the laws of Newton are going to be very important, okay? But it's very, very important that you remember the second law of thermodynamics, to the point that Mr. What's his name? Isaac Asimov wrote a story on how the universe was created, basically, and based that story on the reversal of the entropy. And the reversal of, it's of course fiction, it's not real, okay? And how basically once we discovered how to reverse entropy, somehow we created the universe and everything else in it. And the story that he wrote is called The Last Question. So if you have time, it's not a big story, but it's not a big book or anything like that. It's a short story. So if you have time, read that one. Now, if you are very, very, very strong convictions in your faith and religion, you may want to skip this story because it can shake your faith. So don't do it, okay? But if you, or should I say it the other way around? If you have strong faith, then probably go ahead and read it. So because you should not have any problems. But if you have, yes, yeah. But if you have a little bit of edgy things, so skip what I'm talking about. Okay, the title of his story is The Last Question. Okay, he wrote a lot of sci-fi basically books, but he was a chemist by trade. Okay, so I'm going to stop sharing the screen. Oh, I'm sorry, the recording. Oh, it's still going on. I'm sorry about that.